welcome back on this unit on thermodynamics, and in this is the sixth lecture of this unit, and we have talked about introductory basics, introductions, heat, energy, first law in last few classes, enthalpy and heat capacity as all was discussed. In last class we talked about enthalpy of reaction, enthalpy of formation, enthalpy of phase transition, and we will continue enthalpy of different processes and reaction. Just to recap what we studied about enthalpy of reaction. This enthalpy of reaction at a particular temperature T, we write as AI HM minus BI HM. AI and BI, these are the stoichiometric coefficients for products and reactants respectively, and reaction enthalpy or enthalpy of reaction, standard enthalpy of reaction or standard heat of reactions are generally should be written at a particular temperature, but in case it is not written, then we can assume it to be 25 degrees centigrade, which is the conventional temperature. Now, you showed in the last class that we can get the same information from the enthalpy of formations as well. So, we can write AI for the products minus for the reaction at that reactants at that particular temperature, where del H, this term del F H naught is the enthalpy of formation for that particular species, in this case reactants and products. We also talked about standard enthalpy of formation. In this case, 1 mole of any substance is formed from their reference states at that particular temperature and in standard state of 1 bar pressure. Now, I mentioned this earlier also, that this standard enthalpy of formation or standard heat of formation, the enthalpy and heat for this terminology is very often used interchangeably. So, you can always tell standard heat of reaction or enthalpy of reaction, and for other processes and similarly for other processes as well. We also talked about a standard enthalpy of phase change, like phase transition, like fusion, vaporization, transition and sublimation. We also talked about Hess's law in last lecture, where basically we can take advantage that del H is a state function which depends on initial and final state, which we can break down a reaction of A to B to as many numbers we want. So, if this is del R H 01, this is del R H 02 and this is del R H 03, then the standard heat of reaction for the reaction can be written as the summation of the steps individual reaction. We also talked about thermochemical equation. Thermochemical equation, which is a balanced chemical reaction along with the value of standard reaction enthalpy for that particular reaction, and should be a particular temperature. In this case, we also discuss three important things which should be remembered, that the stoichiometric coefficients represents number of moles of reactants and products. Second, that this standard reaction gives free energy is an extensive quantity, and for reverse reaction the value of standard reaction free energy reaction enthalpy would be negative of the original reaction, okay, with same magnitude. So, these are the some of the things we have discussed in last class, and then we also solved two problems. So, in this lecture we will continue what we left in last lecture. What is that? Now we talked about formation and formation as phase transitions. Now we will talk about other process like combustion and other things. So, first thing we will talk about standard enthalpy of combustion. The symbol is C H naught. At particular temperature you have to, and you have to write the name of the substance you are talking about. So, this is basically the heat of reaction or standard enthalpy of reaction for a combustion reaction. And so, if I take a substance R 1 mole and react with oxygen and produce carbon dioxide and water liquid, and all of these in their standard. So, all reactants and products are in their standard states at temperature T. Then the reaction standard enthalpy of reaction for this particular reaction at temperature T is defined as combustion, standard enthalpy of combustion for that particular substance DNR. One example is glucose combustion. What happens in body, we take this all the carbohydrates which we eat very frequently, it gets converted to glucose, and glucose on react with oxygen, perform a combustion reaction, inside body to produce lot of energy, which is utilized by us to do other work, lot of work. So, we can write glucose combustion reaction like this. Gas remember we are talking about 1 mole. We talked about 1 mole in case of transition, in case of formation, in case of combustion, except in case of reaction we always talking about 1 mole. So, delta S and these are all in their standard state at particular temperature. Say in this case we are not means, so we means 25 degrees centigrade, and so delta for glucose at 298 K is the standard enthalpy of reaction for this particular reaction at 298 K, which is 2802 kilojoules. So, this is the amount of energy we obtain by burning 1 mole of glucose at this temperature. This is what is utilized by us in doing lot of work we do. We will move to now we will solve one problem, and which is given here. It says standard enthalpy of combustion of benzene is given. So, C benzene is given, C6H6 is given as minus 3267 kilojoule per mole, and standard enthalpy of formation is given for carbon dioxide as 393 point. The standard heat of formations, they are tabulated. So, you can get thermodynamic tables from which it is one of them already given in your book. So, you can get these values for lot of substances, this standard heat of formation for lot of substances from any standard textbook, and it is available in literature as well. So, this is very useful data, because as I showed that this can be used for utilizing or getting estimation about the reaction enthalpy for many reactions which is not experimentally determinable, or you can estimate if you want to get. So, these are the data is provided here. So, from that we need to find out the enthalpy of formation of benzene. So, that is what unknown here. So, we need to find out this. So, what is we will do the combustion reaction of benzene. So, as like other combustion reaction, 1 mole combustion, if you want to find out the heat of combustion, we always deal with 1 mole of substance. So, we can write the combustion equation as this. This is a combustion reaction, and because we are dealing with 1 mole of benzene. So, the standard enthalpy of reaction for this particular reaction is what we defined as standard heat of combustion for this particular substance liquid. So, this is the heat of reaction for these reactions, which also named as combustion reaction. You can write heat of reaction, which is given by summation of delta H formations of the products minus, this is what we discussed several times in last two classes, reactants. These are the stoichiometric coefficients, which is the number of moles of reactants and products. So, in case of reactants, this is 1, 15/2, and for products is 6 and 3. So, we can now just replace this term with the numbers in this equation. So, this value is already given as minus 3267. I am not writing the units to make it just to make it our life easier, but you should always write the units, is equal to for products. So, 6 into the value of heat of formation of carbon dioxide, that is minus 393.5, plus 3 into heat of formation of water, which is minus 285.8, minus heat of formation of benzene, which we do not know, C6H6L, minus 15/2 heat of formation of oxygen gas in its standard state. Now, again as I discussed, this is a reference state of oxygen at this condition. So, the value is 0 for heat of formation of oxygen. So, we need to so this term is 0. So, from these 4 terms we can get the value of heat of formation of benzene, and you can rearrange and solve this, and you will find that it is coming around 49 kilojoule per mole. So, here you can see that if you know the heat of formations of the reactants and products, you can get the heat of reaction or enthalpy of standard enthalpy of reactions for any of the reactions involved. And just remind that just a reminder that enthalpy of formation for the compounds or substance in their reference state is 0. So, we talked about enthalpy of standard enthalpy of combustion. Now, we move to next process, which is atomization. So, we will talk about standard enthalpy or heat of atomization. The symbol is delta AT 0, or sometimes is just A, it is written. Atomization is a process where it is a dissociation of a substance. So, atomization is equals to dissociation of a substance into gas phase atoms. So, if I want to write in terms of a equation, so any species, solid, liquid, gas, whatever may be in physical form, 1 mole again in their standard state at particular temperature to the corresponding atoms in gas phase. Here I am not writing repeatedly, this in their standard states, and then at a particular temperature T, and the reaction gives free energy for this particular process is known as the heat of standard heat of atomization or standard enthalpy of atomization. Example, if I take hydrogen gas to gas atoms in gas phase, corresponding heat of reaction for this process, which is also equals to the heat of atomization of hydrogen gas in this temperature. (435 kilojoule per mole). Talk about sodium in solid to sodium atom in gas phase. The standard heat of reaction for this process is again the heat of atomization of sodium solid, value is 4.1 kilojoule per mole. So, we will move to our next problem now. The time is question 12. What we need to find out? The heat of atomization of standard heat of atomization of methane at a particular temperature, say 298 K or 25 degrees centigrade. This is what you need to find out. Supplied the heat of formation of each atom in gas phase, carbon in gas phase and CH4 in gas phase are 218, 716.7 minus 74.8 kilojoule per mole, all at 298 K. So, these are standard heat of formation values for these are supplied. So, we need to find out what is the standard heat of atomization for methane molecule, methane gas. So, the reaction we need to find out. So, we need to find out delta H standard heat of reaction for the following reaction, atomization reaction, which is from the species to their atoms in gas phase. So, we can use the Hess's law and find out from this formation reaction to find out the value of heat of reactions for this particular equation. We can write the heat of formation for hydrogen atom, carbon and CH4. So, we can write start with CH4. So, C graphite plus 2 hydrogen gas, CH4 gas. The value is given minus 74.8. I am not writing the delta H naught value and the unit again. For the second case, which is the carbon gas, carbon atom gas, its formation again it will be from graphite. That is the element in standard state, a reference state, carbon gas. The value is 716.7, and for hydrogen atom in gas stage, reference state is hydrogen gas. So, this is here the formation reaction and the heat of reaction for this is 218. So, the reaction of interest is this one, the atomization of methane. So, methane is in product. So, I can leave this reaction 1 as such, but in this case the carbon gas and hydrogen atom gas is on product side. So, we can reverse this and multiply it by 4 for 4 hydrogen atom, this reaction, to get the final reaction. So, what we will do, we can take reaction 1, we need this in reactant. So, we will multiply by -1 plus we take this reaction, this should be in gaseous form in product. So, we will leave that. So, 2 into 1 plus this again will be products, but in this is 4. So, we have to multiply it the reaction 3 into 4, and then if we add, this will cancel out. So, which will give us the, if we do this, we will find the reaction CH4 gas to C gas plus 4H gas. So, the heat of reaction for this particular may be obtained from this. So, delta E atomization of CH4 gas will be given by -1 into del H formation of F of CH4 plus 1 into del H formation of carbon gas plus 4 into del H formation of hydrogen atom gas, which will come as 1663.5. This will add these numbers, it will come out to be 16 kilojoule per mole. So, again utilizing the heat of formation values and using Hess's law, we can find out the heat of reactions for any other processes. For example, in this case we found out the heat of reactions for atomization process, which is nothing but heat of atomization for the methane gas. Now, we will talk about bond enthalpy. Bond. So, we know chemical reaction is basically formation and breaking of bonds. So, bond breaking plus bond formation. In bond breaking case, energy is supplied. So, energy is given, energy is required, and bond formation always result in energy release. So, energy is released for this case. So, if you talk about thermodynamic terms, the Q would be positive here, because the system requires some energy, and in this case Q would be negative. If you do in a constant pressure, del H would be positive here, del H would be negative here. Now, we can talk about two things when you talk about bond enthalpy. One is bond dissociation in an enthalpy, bond dissociation enthalpy, and second thing is average or mean bond enthalpy. Now, bond dissociation enthalpy is is again, if I write 1, bond dissociation enthalpy is excuse me, bond dissociation is the change in enthalpy when again 1 mole. Okay. In this case also we are talking about 1 mole of covalent bond bonds of a gaseous covalent compound is broken to form products in gas phase. Okay, not any other phase, but in gas phase. So, if you talk about diatomic molecules first, let us talk about diatomic molecules first. Diatomic molecules, like examples we have given hydrogen gas. So, this is the bond dissociation enthalpy is the change in enthalpy when 1 mole of covalent bond in a gaseous covalent compound. In this case, hydrogen gas is a gaseous covalent compound. We are taking 1 mole and is broken into products in gaseous phase. So, in this case the products which is hydrogen atom is also in gaseous phase. So, this is the bond dissociation energy for bond dissociation enthalpy for hydrogen gas. So, we can write hydrogen bond dissociation enthalpy, which is given by the value is this. Now, this is the same value for the standard enthalpy of atomization, because this is exactly atomization reaction for hydrogen gas. So, for diatomic molecules in gaseous phase, see the atomic molecule in gaseous phase, the standard enthalpy of atomization is equivalent to the bond dissociation energy for that particular substance. This is true for diatomic molecules which are at gaseous phase. Now, we will talk about polyatomic molecule. Now, in case of polyatomic molecules, the bond dissociation energy is if you talk about say CH4. Now, if you talk about there are 4 CH bonds here, the bond dissociation enthalpy for these 4 CH bonds are if you talk separately CH they will be same, but when you dissociate, you will dissociate one after one. So, as a result, this CH bonds enthalpies will have different values. So, we will get a mean value for all these bond enthalpies. So, for CH4 gas, if we consider that all the bonds are broken and you get the product in gas phase, then this is the reaction standard enthalpy of this particular reaction, which is also known as the standard heat of atomization for methane in this particular case, which has a value of 1665 kilojoule per mole. You can consider the bond energy for or bond average or mean bond length, mean bond enthalpy for this molecule CH4 as 1/4 of this particular value. We might just elaborate little bit if how the individual molecules. So, if you take CH4 and get, I am just not writing the gas and all this thing, make it short. So, you have to remember this is all in gas phase. I am not writing just to make it simpler. This is 427 kilojoule per mole, and next CH3 to CH2 H, this is 439, this is 452, and so all the four, when we removing one after one, when we breaking one after one, these all have different values. So, all the four bonds have different standard bond dissociation enthalpy. So, mean bond enthalpy for this case, mean bond enthalpy standard value of course in CH4 gas is given by delta CH is half 1/4 of this atomization reaction, total overall atomization reaction of CH4 gas, half of 1665, approximately 416 kilojoule per mole. Now, mean bond enthalpy for some bonds, if you talk about same bonds in different compound, like carbon hydrogen bond in different compounds like methane or ethane or methanol or ethanol, they could be slightly variable, the value could be slightly variable when you compare the same bond in different compounds. Now, what we will do, we will talk about next okay, we have talked about this bond dissociation enthalpies and then mean bond enthalpies. Now, some gas phase reaction, especially we talked about that any reaction enthalpies can be obtained from delta F formation values of reactants and products. Now, some cases these values, especially in gaseous phase, is not available. The delta H formation for some cases is not available. Then this mean bond enthalpy or the bond dissociation enthalpy come handy to get the reaction enthalpy or standard enthalpy of reaction. So, if you consider a gas phase reaction, we can write just general form reactants to products, that is our reaction. Now, what we can think of this, instead of directly reactants and forming products, reactants bonds are broken into the atoms in gas phase and then form those atoms in the gas phase, product is formed. So, we can write two different, we can break this into two different reactions. One is the reactants to atoms, all in gas phase. I am not writing gas phase again and again. Now, in this case it will be the summation of the bond enthalpy, because reactions are getting broken into the gas phase reaction. That is what we defined the bond energy. So, if you look at the bond dissociation enthalpies, where a molecule is broken into the gas phase product. So, in this case we can write this as the summation of bond enthalpies of the reactants. Now, we can talk about take these same atoms in gas phase and make products from this. So, in this case it is a reverse of bond dissociation enthalpies. So, in this case the standard enthalpy of reaction, this would be reverse or negative of bond enthalpies of summation of bond enthalpies of the products. Now, if we add this to reaction, then this intermediate cancels out. So, we get back our reactions from reactants to product. So, the delta H R, the standard heat of reaction, now can be obtained from summation of the bond enthalpies of reactants minus summation of the bond enthalpies of products. So, if we know the values of all the bond enthalpies of the individual reactants and bond enthalpies for all the products, then we will be able to, from the values for this, we can able to get the enthalpy standard enthalpy of the reaction for this for our reaction of interest. This is very useful for chemical engineers when they estimate the reaction enthalpy or standard enthalpy of reaction. They can get the data from bond enthalpies. Now, we will talk about the next process, which is enthalpy of solution or heat of solution, and the symbol is solution H naught. So, the process is solute again 1 mole to solution in specified amount of solvents. So, if you have different amount of solvents, the value of this delta R H for this reaction, which is known as delta enthalpy of solution, could be different if we use different amount of solvents. For example, if we take example of HCl gas, if we dissolve in 25 moles of H2 liquid, then we get a solution, and delta R standard heat of reaction for this reaction is minus 72.3 kilojoule per mole. And if we take HCl gas and 40 H2, 40 moles of H2, we get another solution where the value is 73.18 kilojoule per mole. And if you take gas, this is gas plus infinite amount of H2O. We will explain what is infinite amount of H2O means. We write HCl in aqueous state, which is given by 75.14 kilojoule per mole. Now, when you talk about infinite dilution means, if we add, if we have a solution where if we add further solvent and we found there is no change in heat or there is no heat change associated for dilution, then we know we have reached a sort of infinite dilution. So, if you find that no change or no exchange of heat associated with dilution, heat if we add further solvent, in this case H2, if we find that is no change in the delta H value, then we call this is a infinite dilution. In this case, sometimes these are, in these two cases, these are called differential heat of solution or enthalpy of solution, and in this case we call, in this case we call integral heat of solution, and in this case we talk about differential heat of solution, but that is not of your topic, is not part of your syllabus. So, we will talk about heat of solution, and that will depend upon the amount of solvent we use. For ionic compounds, little we need is basically little special for ionic compounds. So, we take simple AB as solid, and now AB salt will be it will be constituted by some ions, and the constituent ions are in ordered state when they are in solid form, in ordered crystal lattice. So, if you do a dissolution process, then what will happen? The ions will be solvated, will be surrounded by solvent molecules when they are in solubilized in a solvent. Now, typically we use water as a solvent, then we can call this as a hydrated, and we can write AQ as a aqueous medium as a solvent. Now, to get this, if we use solvent is water. Now, we can get this value indirectly, like we explained earlier. So, this is delta solution, standard heat of solution, when we have the dissociated ions in solvated or hydrated. In this case, we can get into the ions in gaseous form, why I am writing plus, this minus. Gaseous form, and then we can solvate or hydrate this to get into solution. So, this is delta H lattice energy, and this is hydration, standard heat of hydration, and this is standard heat of standard lattice energy or standard enthalpy of in the lattice. So, for most of the ionic compounds, delta solution is positive value, because you have to apply or you have to supply lot of energy to basically dissociate these ions from or separate the ions in a lattice. So, basically generally we increase with increase in temperature, the solubility goes up, because it is a endothermic, the solution process is solubilization process is endothermic, solubility goes up, increases. Now, the ionic compounds to ions in gaseous state, this enthalpy of reaction, the standard enthalpy of reaction is called lattice, standard lattice energy for one mole of ionic compound. So, if mx is my general structure, 1 mole, if I take in gaseous state plus x minus in gaseous state, then the delta R H naught or standard heat of reaction for this process will be the lattice enthalpy for mx. So, for example, we can take NaCl solid, we can talk about Na plus in gaseous state plus chloride gaseous state, delta R H for this reaction, which is so that is the lattice enthalpy for NaCl. Now, we can indirectly, we don't, we will get we can get this experimental value of lattice enthalpy. The experimental value of lattice enthalpy can be are obtained, generally are obtained by using a cycler reaction called Born-Haber cycle, which is a closed path of transformation starting and ending at the same point, and one step in this cycle, is of which of the cycle is the formation of solid compounds from a gas of widely separated ions. So, we will take example of KCl in this case. KCl, so our lattice energy would be KCl solid to Ka plus gas plus Cl minus. Now, we can start with a KCl solid and then first we move to corresponding dissociated steps. So, this is basically reverse of the formation reaction. So, this is minus del H F of KCl solid, because these are the reference states for constituent elements of KCl, and the value for this process would be 437. I am not writing the units once again. Now, K solid would be now transformed to K gas. So, it will be the sublimation enthalpy of K solid, which is value is 89, and chlorine would be again dissociate to chlorine atom gas. So, it will be half of dissociation energy of chlorine gas, which is 122. Now, this K gas will be converted to say K plus gas. This is a reaction, standard reaction enthalpy for ionization enthalpy. Value is 418, and it will take up electron to form chlorine gas. So, it is electron gain enthalpy, delta R H is electron gain enthalpy. The value is 349. From here we can form. So, this is the ions in gaseous phase. So, reverse of this reaction. So, we get minus of lattice of KCl. So, this is a cyclic process. So, the total del H for this process, cyclic process, should be 0. So, now we can add all this value to get the value for this unknown. So, this is known as Born-Haber cycle. So, using this, basically you are talking about a cyclic process. With this we can get the value for this. So, we can just write 437, we can add these numbers 89, 122, 418 minus 349 minus this del lattice H0 of KCl. So, from there you can get this value to be 717 kilojoule per mole. So, with this I will stop in this lecture. So, this basically mostly covered the thermochemistry part, and Next class I will talk about the other rest of the part of your thermodynamics unit, which talked about the criteria for spontaneity for different processes we just talked about.